Good morning, guys. Sorry I can't be here today. We're going to just continue on with number patterns, and we're going to talk about a geometric sequence. Make sure you've checked your homework on arithmetic sequences. And today's day 3, so don't forget, next class is when we have our quiz. Alright, a geometric sequence is one where the ratio between two consecutive terms is constant, and it's called little r. So to find the ratio, take any term and divide it by the previous term. So here's an example of some patterns. Is it a common ratio? Is it geometric? So from 15 to negative 30 is timesing by negative 2, but 30 to 45 is timesing by 1.5. So no, not geometric because it's not the same ratio. Going from 1 to negative 2/3, that's multiplication by negative 2/3. If you multiply by negative 2/3 again, you get 4/9. So yes, and the ratio is negative 2/3. That's what you're multiplying by every time. For this pattern, 2 to 4 to 8, that's times 2. X to x squared is times x, so that's multiplied by 2x. That's multiplied by 2x. So yes, it's a geometric pattern, and the r is 2x. Okay, so if you don't have the list of numbers, but you have the rule, you do it the same way we did with arithmetic. You plug 1 in, plug 2 in, plug 3 in, etc. So if I plug in 1, I'm going to get 2 to the negative 1. 2 is 2 to the negative 2. 3 is 2 to the negative 3. So my pattern is 1/2, 1/4, 1/8. 1/2, 1/4, 1/8, and it'll continue in that vein. And so to show that it's geometric, you have to show that the ratio here is the same as the ratio here. So you can show that by doing 1/4 divided by 1/2 is equal to 1/2, and 1/8 divided by 1/4 is also equal to 1/2. So ratio stays the same, which means geometric. Okay, what about this pattern? We're going from 8 to 16. That's times 2. We're going from b to b squared. That's times b. And this is also times 2b. Okay, so to find the 6th term, for this one, it's probably just as quick for me to do it by hand. So times 2, times 2, times 2. How many am I doing? This is 1, 2, 3, 4, 5, 6th term. So that's it. Okay, and you notice that the powers of b match the placement, so I should be at b to the 6th. And I timesed it by 2. Just remember this from last time. To get to the 6th term, I timesed by 2 5 times. 1, 2, 3, 4. All right, I multiplied by 2 5 times to get to the 6th term. Okay. X plus 6, and 2x plus 3 are consecutive terms of a geometric sequence. So, because it's geometric, that means the ratio has to stay the same. So, from an x to an x plus 6, that ratio has to be the same as from an x plus 6 to a 2x plus 3. So this ratio has to be the same as this ratio for it to be geometric. Okay, so a little algebra here. It's kind of cool. Problem. Square the binomial. Square double product square. distribute the x. Put everybody on both sides, so minus him over, minus him over, minus him over. So I'm going to get x squared minus 9x minus 36. Factor. Factors of 36. 6 and 6, no. 9 and 4, no. 12 and 3. Okay, and the question is, find the value of x. Could be leading off with the -3, or could be leading off with a 12. And they both will make a number pattern that's geometric. Okay, so here's a new pattern. 2 to 4 to 8 to 16. This is times 2 times 2 times 2. So how could I figure out the 9th term? Well, 9th term, how do I figure it out? Well, two options. I say, all right, I'm starting on a 2, and I'm multiplying by 2. How many times? 8 times. Because to get to the 9th term, I need to make 8 jumps. Okay, so I don't know what 2 to the 9th is, but it's a big number. Let's see. Calculator. Let me see if it's too big. 2 to the 9th. 512. All right, what if this is the pattern? 2 to 6 to 18 to 54. This is times 3, this is times 3, this is times 3. So I have to do times 3 8 times, right, to get to the 9th term. So times 3 times 3 times 3 times 3, 8 times. But what times 3? Well, I started on a 2, and I times it by 3, and then times it by 3, times it by 3. So that would be 3 to the 8th, times 2, 13122. 13122. So in general, here's the formula. To find any term, okay, sometimes called the nth term, or sometimes you'll just say any, to find any term, you start on the first term, and you multiply by r, which is the common ratio, and you do it n minus 1 times, because n minus 1 times gives you the number of jumps. N is the position number, but to get there you need to make 1 less jump. Okay? So write a formula for this pattern. So you're given A1, you're given R, right? R is from 8 to a 4 is times 1/2. 4 to a 2 times 1/2. So a general formula for any term would be start on an 8, multiply by 1/2, n minus 1 times. That's a general formula. So general formula means with n in it. Then second part, use your formula to actually figure out A8. So starting with an 8, multiply by 1/2, 8 minus 1 times. So that's 8 times 1/2 to the 7th power. And that is 1/16. And I just thought of something kind of cool. How I could have done that without my calculator. So 8 is 2 to the 3rd. Remember, this is kind of like our same basis. 8 is 2 to the 3rd, and 1/2 is 2 to the -1 to the 7th. So that's 2 to the third, 2 to the negative 7, so 2 to the negative 4, 1 over 16. Okay, but you can use your calculator. I just thought that was cool. But then again, I think math is cool. All right, another example. If A1 is 4, given, and R is 0.1, given, write the first 3 terms of the sequence. So it starts out with 4, multiply it by 0.1, multiply it by 0.1, okay, keeps going. Find the 10th term. So A10 is A1 times R to the n minus 1. 0.1 to the 9th. So 0.1 to the 9th. That's a 1 with 8 zeros in front of it times 4. 4 times 10 to the negative 9th. And your calculator can do the scientific notation for you if you can't remember how to do that. Okay. Another example, a lot of examples here. Find the first term. Okay, so you don't know A1. If the common ratio is 2, okay, so make a little list of what you know. You know A1. No, you're trying to find A1. You know the common ratio is 2. You know the 6th term is 96. Okay, let me just jot down the formula here. Okay, I know that I'm ending on a 96. Don't know what I'm starting on. My R is 2. And to the 6 minus 1 power. So 96 is A1 times 2 to the 5th. Whoops. And 2 to the 5th is 32. Divide over the 32. 3. Okay, so the first term is a 3. Okay. Another example. What is the common ratio? So you're trying to find R. So if you're given the equation, this right here is the R. Okay, so the R is 3. Find the third term. So I noticed in this one, it doesn't always have to be an A. So this one they changed the variable to T, term. It doesn't matter. Third term would be T3, which I would get by plugging in a 3. So this would be 3 squared, this would be 9. Okay, the third term is 45. So just want you to be able to interpret this formula for a second. So the first term, see how the 5 is right there? That's what you would get by plugging in a 1. So it starts off with a 5. Then you're timesing by 3, timesing by 3, timesing by 3. So that's how you interpret it when the rule is given to you. The number raised to the power is the ratio. The number in the front is the first term. All right, same thing from last time to this time. You don't always need to know the first term. So this says A6 is a 48. Okay, this is in the 6th spot. The 7th spot is a 24. All right, so just knowing those two, you know that the R is 1/2. So you can do this a couple of ways. You can just back it up, 5, 4, 3, 2, 1. Back it up by hand. You can use the formula. Realistically, what are you going to do? I'm thinking most of you are just going to back it up by hand. So this guy was a 96. Oh man, these numbers are going to get big. This guy was a 192. This guy was a 384. 768. 1536. So 1536 times 1/2, just checking it, 1536, so start here. If I multiply that by 1/2 to the 1, 2, 3, 4, 5, 6 power, because 6 jumps, I end up on that 24. Okay, so I just checked it. I'm curious if anyone would have used the formula. Should I show you that? The formula might have been a little easier on that. So here's the formula. AN equals A1R to the n minus 1. I know that A7 is a 24, so I end on a 24. I don't know what I start with. I know my R is 1/2, and I know I made 6 jumps. And 1/2 to the 6th is 1/64. So to get that A1, I'm going to multiply 24 times 64. 1536. I think that was almost a little bit easier. Alright, application problem. So initially a pendulum swings through an arc of 18 inches. So here's my pendulum. You swing it and it goes like that, and that's 18 inches. Okay, on each successive swing, it shortens because you've got gravity pulling it down. And on each successive swing, it's 0.98 of the previous length. So that's the R. So on the second swing, it was 18. On the second swing, it's 0.98 of that, which is 17.64. Okay, on the 10th swing, so how many times am I multiplying it by 0.98? Remember, this was the second swing. So on the 10th swing, I need to multiply it by 0.98 9 times. So that's going to give you 15.007. I don't know how accurate you need to be. Doesn't say. And so kind of our general rule that we're figuring out here is the length of the swing is 18 times 0.98 to the n minus 1. That's sort of our general rule we're using. On which swing, so that means we don't know n, will the length first be less than 12? So 12 here. All right, and I don't know n, but I want it to come out 12. Well, a little bit less than 12. So divide by 18. 12 divided by 18, decimal, 2/3. Okay, how am I going to get the n down? Well, I'm going to log both sides. And the n minus 1 is going to come down. Okay, and then for the algebra here, what I'm going to do is I'm going to take the log of 2/3. I'm going to divide over the log of 0.98. That's n minus 1. And so then I'm going to add 1 to it. So grab your calculator, see if you can get this. I'm going to use my alpha y equals to make a fraction. So I know that I've got log of 2/3 on the top, log of 0.98 on the bottom, add 1 to it. So I get 21.07. So which swing is it? So on the 21st swing, because I don't know if I'm rounding up or down, on the 21st swing, I would be at 12.02. So it's not less than 12. So I need to go to the 22nd swing. That gives me 11.8. So the 22nd swing. Cool. All right, hang in there. One more concept. Again with the mean. The mean is missing terms between given terms. So you can do this, you know, with the formula. You can do it logic. Let me try. I'll show you a couple of each. So for this first one, 20 to something to 80. Now remember, you're multiplying. I think most people, you can figure out that you'd be multiplying by 2. And if you're multiplying by 2, then the missing number will be a 40, right? 20 times 2 is 40. But because it goes positive blank positive, you also might be multiplying by a negative 2. And there's no way for you to tell. It could be a negative 40 there. Because if you have 20 multiplied by negative 2, you're going to get negative 40. Multiplied by another negative 2, you're going to go to positive 80. So you have no way of knowing if that missing term is positive or negative. And that's just something kind of interesting. Okay, let's try to figure out this one. With the should we do it with the formula, or let's try to do this one just logically. So from a 48 to a 192 is times 4. So you have to have this jump be also times 4. So that tells you that it was a 12. All right, if you don't see that, you can always use the formula. All right, because it's kind of like logic, or use the formula. This one, all right, we got blank blank 3, blank blank 1/9. Let's try using the formula on this one. So again, it doesn't matter that I don't know these first two terms. I can just start here. So call him A1. 1, 2, 3, 4. Call him A4, because it doesn't matter where in the series I look. So the formula would say I'm ending on a 1/9, starting on a 3. I don't know my R, 2, 3, but I have 4 minus 1, 3 jumps. Okay, so divide over the 3, you're going to get 1/27. Cube root both sides, you're going to get 1/3. So that means 3 times 1/3 would bring me to a 1. Times 1/3 again, that would bring me to a 1/3. Times 1/3 again, that would bring me to a 1/9. So if you were going to back it up, you've got to multiply by 3 to go backwards. Multiply by 3, multiply by 3. Okay, I'm not saying you couldn't have figured that one out without the formula, but I just want to show you the formula will always work. Okay, let's tie this together with something we already know. The graphs of a geometric sequence are exponential. Okay, and when we say little r, we used to call this, back in exponentials, we called it the growth factor. And we called it little b. Okay, so here's an example. If I were to orient these numbers vertically, 3, 6, 12, 24, and I were to make a graph of it, 1, 2, this is n, and this is 3, 6, 9, 12, 15, 18, 21, 24. I'm going to go by 3's here. 3, 6, 9, 12, 15, 18, 21, 24. And I were to graph these numbers, plot these points. 2 gives me 6, 3 gives me 12, 4 gives me 24. The graph is exponential. Okay, so if you were to look at this exponential and you were to think about, so go back up here for a second. Think, our old general form for an exponential was y equals a b to the x. Okay, can you see how that's pretty much the same as an equals a1 r to the n minus 1? Same format. So how you would write the rule for this. So you can be thinking, so let's first think about exponentials. Okay, so just think about our old stuff. Y equals a times b to the x. So for this scenario, the y is really an, A is the starting number, which is 3. B is the common ratio that I'm going up by. I'm doubling every time. And N, and X is N minus 1. So do you see the similarities between our old form and our new form? If you were to plug a 1 in for the N, you'd get a 3. If you were to plug a 2 in, you'd get a 6. Okay, what would it look like recursively? Well, I'm starting on a 3. Any term is the previous term times 2. So that would generate a 3, and then a 6, and then a 12. Okay. Let's look at the second example. What if the terms are going down? 27 to 9 to 3 to 1/3. 27, 9. So let me go 3, 6, 9. Nope, that's going to be not enough room to get to 27. 3, 6, 9, 12, 15, 18, 21, 24, 27. 12, 9, 6, 3. Is that good? 3, 6, 9, 12, 15, 18, 21, 24, 27. Starting at the 27, dropping down all the way to 9, dropping down to 3, dropping down to 1/3. Oops. Okay, so that's exponential. It's just exponential decay instead of exponential growth. Right, so everything we learn from the exponential units is related to geometric sequences. And everything you've ever learned about lines is applicable to arithmetic sequences. And quadratics, parabolas, they're related to another sequence called the quadratic sequence, but we're not gonna do that in this course. All right, hope that was okay. You can go ahead and start on your homework.